So everybody, welcome to our Introduction Networks meeting for, I guess, Election Day, November 3rd. I hope everyone is doing well and safe and having a good day. I want to talk a little bit today about a couple things. First off, I had, I believe, Sharif email me asking about grading. I'm catching up on grading. So I'm still trying to get that done. I'm not caught up with any of you. So I'm working on that. That's on my agenda to continue through the week. So hopefully I'll get the grading caught up before we meet again. So but I am a little behind on grading, so I ask that you just know I am trying to catch up, so it shouldn't take me too long to get caught up with it. Second thing I want to talk about is we have been talking a great deal about subnetting and subnetting based on what I call a classful subnetting. So we're using the same mask across all subnets. Now, this is classful, even though it is a class A and we borrowed 8 bits from it. But the reason this is considered more classful than classless is because we're using the same subnet size for every single subnet. So we've got all these 256 possible subnets, each one of them with 65,534 hosts. That, however, is not extremely useful out in the real world, because out in the real world, what we're going to want to do is we're going to want to make our subnets meet the needs of our networks, which forces us to back up just a little bit and think of things differently from the 7 holy steps of subnetting. Now, the reason being is because with the 7 holy steps of subnetting, we were solving for, if you remember, our formula was 2 raised to the n power, which equaled the number of subnets. Well, the problem when we get into Vlsm is now we're going to look at the number of hosts, not the number of subnets. So we need to build subnets to support X number of hosts. To do this, we have to remember our formula 2 to the H minus 2, which equals the number of usable hosts, where H equals the number of host bits. Okay. So we're going to want to kind of change the way we're doing things now, instead of looking at trying to use the same slash notation across everything. Now, one of the things that this particular example gives you is we're going to start out with what would be traditionally a class C, this 192.168.20.0/24. And the way the curriculum teaches you to solve VLSM problems is it says, find the largest subnet that you need in terms of number of hosts and subnet out to that level. So let's think about this. If we needed to leave at least 28 hosts, we look at our formula here, okay, what will we need in terms of leaving our bits? Okay, what power of 2 would we raise to 2 in order to leave at least 28 hosts? It'd be 5, wouldn't it? Which equals, that'd be 32 for a total of 30. So we're going to look now, we're not solving using our number of subnets, we're solving for our number of host bits. So we look at this, this is a class C. And even if it wasn't a class C, if this happened to be, for instance, by the way, 10.0.0.0, excuse me, can't type today. If it happened to be this, okay, it would make no difference whatsoever, because we know with this /24, that just means we've got 8 host bits to play with. So we've got 8 host bits here to play with. We've got to leave at least 5 of them in order to allow us to have 30 hosts per network. Now, you also notice here, because this building C needs 15 hosts, if we were to leave, if we go one more and say 2 to the 6th, or 2 to the 4th, 2 to the 4th is 16 minus 2, which is actually 14 usable hosts. So we really can't go any smaller than this borrowing 5 bits. Otherwise, we won't have enough for this building C's host right here. So what we could do then is we take and we say, okay, we need to leave 5 bits as zeros. So that means we can borrow up to 3 bits. All right. And that then tells us that since we borrowed 3 bits, our variable in this octet would be, or our magic number is now 32. And so you get these subnets. You get 0 to 32 to 64 to 96 /27 all the way across. And what they're doing here then is they're going to say, we're going to use these for building A, B, C, and D. Now, this is perfectly fine. This is how the curriculum teaches it. I would not do it this way. I would do something slightly different. I would actually have pulled out this 32, 64, 96, and 127 to be my building A, B, C, and D. And then I would have subnetted again this 20.0. So if we go down here and look what they're doing with this, they said, okay, we're going to give the .0 to A /27, the dot 32 to B, C, and D. And then they were leaving, in this case, they tried to use non-variable length subnet masking. So they just left the /27. But by pulling out the first 4, it makes it much more difficult for you on your point-to-point links. And I'll show you why in just a second. So we've got this, but let's go down and look at Vlsm and say, okay, we're going to do the same thing, but we're going to change it slightly. We're going to, instead of taking and leaving everything /27, we're going to use Vlsm. And by the way, Vlsm, if you really want to think about it, is simply subnetting a subnet. So we pulled out the .20.0 /27 right here. We pulled out the 32, the 64, and the 96, and that becomes lands A, B, C, and D. We then go, and what they do is they go all the way down to the last subnets available, this number 7 here, and they subnet it again. So in other words, they go ahead and borrow. They know they only need to leave 2 host bits. So they go all the way down and they borrow down to there's only 2 host bits left, which makes your variable 4. And then they break this 224 down into these /30s, 224, 228, 232. Now here's the reason I don't like this. The 2 usable addresses here are 225 and 226. Of course, 224 is the network ID, 227 is the broadcast ID, and then 220. That's crazy. What I would have done is this, okay? So let's look at this and say, okay, Kelly did this. So I first would have done exactly what they did here, but I would have said, okay, for LAN A, let's use the network 192.168.20.32 /27. Okay. For LAN B, we're going to use 192.168.20.64 /27. C, we're going to use 20.96 /27. And then for D, we'll take 20.128 /27. Now you notice I didn't use the first subnet. I did not touch this network that we'd already pulled, 192.168.20.0 /27. And the reason I didn't is because what I'm going to do now is I'm going to go ahead and subnet it again. By the way, let's imagine, using just a magic number formula, let's say this is /now 28. What is our variable if we borrow 1 more bit? Anybody? What would the magic number be if we borrowed 1 more? If you borrow 3, it's 32. So if you borrowed 1 more, the magic number would be
16.
Anybody?
16.
16.
Yeah, 16. Yeah.
16. Okay. So what we're going to do then is we're going to take this /27 and borrow 1 more bit, and we'll make it 0 to 15 and 16 to 31. So we just broke this network. Okay, this subnet, we subnetted it again. So we're subnetting a subnet. Then we're going to go down here and say, okay, well, I'm going to go ahead and do a /29. And I'm going to know now that my variable was 16. Now my variable is 8. So let's take the 0 to 15 and we'll go 0 to 7. And then 8 to 15. And you'll notice I'm not even going to touch this one right here. I'm going to leave it because I might need a /28 network somewhere. So, but I'm not going to even touch this. I'm going to go out here and say, okay, well, I'm going to borrow one more bit because I know these are networks of more than 2 hosts. So I'm going to go out here and do a /30 now. And I'm going to go, all right, so let's take this and we'll take the 0 to 7. And that becomes 0 to 3, 4 to 7. And then this, we're going to also break into 2 pieces, becomes 8 to 11 and 12 to 15. Okay, 0, 4, 8, 12. These are all /30s. And so now I would put 192.168.20.0/30 between R1 and R2. And I could put .1, .2 here. I would then put 192.168.20.4/30 right here. 5 and 6 would be my usable numbers. And then I would pull .8/30 and 9 and 10 would be my usable numbers here. The reason I do this is because if you're using these as your /30s, it's so much easier to remember. 0, 4, 8, 12, 16, 20, 24, 28, 32, versus trying to pull these crazy numbers they've got out here, like this 224, 228, 232. Real world, you'll also find that most people try to do their WAN links or their point-to-point links. They try to make the /30s some of the first addresses in the network. However, I must warn you, all of your packet tracers, all of them assume that you're going to do exactly what is shown here, that you're going to pull the biggest networks first from the lowest portions, and then you will find your other portions from the leftover subnets. You need to be extremely careful with your students on this because there's multiple ways of doing this and it would still be correct. So if I did this, if a student turned this in right here, if they subnetted this and used these subnets for A, B, C, and D, and then pulled these out right here for, and in this case, it'd be the .0, .4, and .8 for their point-to-point links, they are correct, even though Packet Tracer would not give them credit for it because of the Packet Tracer having to be very, very specific. So one of the things for you as you're grading VLSMs is always look to see if the / notation is correct. If it is correct, then go to look to make sure they're not overlapping anywhere. By the way, if I assign this to a network or to a point-to-point link, I cannot use this and I cannot use this, because to try to use any part of this again after I've assigned this /30 would be what's called an overlapping network. So if you've ever accidentally got that and it said you cannot assign it because the networks overlap, that's exactly why. Questions? Okay, so let me just do this real quickly here. I'll pull these out and I'll pull out a couple switches real quick. I really didn't need that second switch. I just want to show you what you'll get so that you'll, so if we do gig 001 be inside, and we'll do gig outside here. Let's just do nope. Okay, int, gotta go global config, big T, int gi00/0. I'm gonna do IP add 192.168.20.2 255.255.255.252. By the way, that is a /30 mask. No shut. All right, so I brought up, and I'm gonna do host name of R2. Do right. All right, so he's done. So I'm gonna go over here on R1. En config config T host R1 int gi000. By the way, a lot of times when I'm doing my own examples, I always use 000 as the outside because it's an O, and I use 001 as the inside, just for simplicity's sake. No shut, and we should be able to do right. Control Z, and we should be able to ping from R1 to R2. Oops. If you don't do something like that and forget to put the other IP address in. There it goes. So we got pingage between R1 and R2. But now I'm going to go in here and I'm going to go to my inside interface, config T, and I'm going to go int gi001. Okay. And I'm going to try to put in the IP address of 192.168.20. And let's go look at our example here. So let's do, we've only got 0 to 1 here. So I'm just going to try to do dot 3 255.255.255.0, and you'll see if you spell it right, you should get an invalid address because it overlaps. Okay, because I've tried to put this dot 3 with a /24 is part of or overlaps with my dot 0/30. But I could go in here and put, if I wanted, okay, 33 with a mask of 224/27, no problem whatsoever. Do another shut. Do show IP int brief. You will see now that I've got 2 IP addresses. Again, unfortunately, it doesn't show you the mask here. To show that, you got to do a show run or show gi000, and we'll tell you that's a /30. This one is a /27. But you'll notice those no longer overlap because the .32/27 and the .0/30 do not overlap at all. So you don't get that overlap message. So if you ever see that, if you get the message you're overlapped, it just means you probably are using the wrong mask on one of your different interfaces. Any of you seen that during your work in the curriculum?
I saw it one time. I can't remember exactly when it was. It's been a while. Probably the first couple times I was using the plan.
Okay. It's very common to happen, and it's very common for your students to do this too. Very, very common. But again, remember, they are always going to pull, they're going to pull the major big blocks out from the very first subnets. And then they're going to pick another one higher up to become the /30s. I don't like that. I just like the /30s to be low. Most people in the real world do the same. So, but here's their example of assigning the Vlsm. You'll notice they put all the /27s across the buildings here, and the /30s starting with 224, 228, 232 between the point-to-point links. And you end up with those addresses as a completed table. So Vlsm is just subnetting a subnet. That's all it is. We take our largest, find out what we need from that, and then go from there. So let's imagine, I just want to throw one out here. I'm going to give you an easy, let's imagine that we've got just a LAN A, and it needs 100 hosts. LAN B needs 30 hosts. And then you need one point-to-point link. Okay, so imagine basically this network right here, and we need 100 hosts on the left. By the way, you can, if you ever wanted to do your own, you can actually go in here and put in information, if I can remember where it's at. No, that's not it. Cannot for the life of me now remember how to put it in, but you can actually build your own and put your own in here. internal. Okay. So let's imagine that. So we've got this, and we've got the network. Oops, let's actually do this down here. Let's just do 10.0.0.0/24. What I would do, obviously we need 100 hosts. Okay. So the first thing I do is how many host bits do I need to leave in order to get 100 hosts? So 2 raised to what power minus 2 equals 100 hosts, or at least 100 hosts. Anybody?
2 to the 7.
2 would have to equal that exactly. H would have to equal 7, and that would be 128 minus 2, which would be 126. Okay. So if it's 2 to the 7th, that means we're only going to borrow 1 bit because we have to leave 8 host bits. And then our variable then, or our magic number, is 128. So we would take this here, this one network, and we would borrow 1 bit, and we would break this into 2 subnets, and I'm gonna be lazy because we know we're only working in the 4-octet, of 0 to 127 and 128 to 255. Now what I would do is I would then go up here and I would assign 192.168. Excuse me, there I go, screwing up again. 10.0.0.0, excuse me, 128/25 is what I would put for LAN A. And then this is being used then. So we know that that is now used. So we can't use it for anything else. It's taken apart. Okay, it might be a little easier to see. So this one's been used, but we've still got this entire subnet that we can use for LAN B. So let's go ahead and say, okay, well, let's borrow another bit, /26, which means now if we look down here, /26 means we've got 1, 2, 3, 4, 5, 6, 7, 8. Our magic number becomes 32, excuse me, 64. So this is 0 to 63. And then it is .64 to .127. Notice I'm not making numbers up. I'm just using what's already there and breaking it into 2 pieces. Okay, by the variable. How many hosts are there on each one of these subnets?
62.
If you got a /26. Well, let's look. We've got 2 to the 6th power.
62.
62,
right?
exactly. So this is still a little bit bigger than what we need to meet LAN B's requirements. So we just subnet the subnet again, /27. And we'll take, and for me, I would leave the 64 alone and just take this one here. Now we know that since it's a /27, it's 111, 2, 3, 4, 5, 6, 7, 8. Okay, so now the variable is 32. So it's .0 to .31 and .32 to .63. Now at this point, this is a network of 30 hosts. Both of these are subnets. So I would come up here and say, all right, we're going to take this, and this will be 10.0.0.32/27. And now here's the beauty. Here's the beauty of my system. Because I'm lazy, I know I can automatically do this right here. 10.0.0.0/30. I don't even have to subnet this out anymore because I know that that's not being used. But if I wanted to, I could go in here and just do /28. Okay. And then this becomes obviously .0 to .15 and .16 to .31. And we could go again, /29. And we come in here, this becomes .0 to .7 and .8 to .15 And then finally, last but not least, we go all the way down to /30. And we're just going to have .0 to .3 and .4 to .7. And so we could just pull that piece out. But doing it the way I do it, I didn't even have to do all that because I knew I could just go straight all the way to .0/30, .4/30, .8, .12, all the way up to, I just couldn't go anywhere, couldn't go past 32 because I've already pulled this part out to be used here. Okay. So does that make sense? You're seeing we're just subnetting a subnet. And then we pick, the beauty of it is we pick and pull the pieces to match whatever network we have, whatever our host networks size are, which is really nice. Okay. Questions about that? And then there's a whole bunch of different things about structure, design, and planning. And one of the things you do need to know about with planning of different IP addresses. There's a book world and there's a real world. Now I'm going to tell you, in the book world, if I was asked and I had a test question and it said you needed 100 hosts and you needed 30 hosts and you needed this, I'm going to subnet it to meet this requirement exactly for the book world and for the test world. Real world, folks, hosts are like rabbits. You got 30 today, you'll have 60 tomorrow for the most part. So I would be very careful if I was actually building this real network to have used a /27 on a network that already has 30 hosts on it, because more than likely, that's all a /27 will support is 30 hosts. As soon as I need another host, then I'm going to have to completely renumber my network, which can be problematic to say the least. So in the real world, teach your students to, I usually say, account for about 30% growth. That's not always true, but I like to have some overhead simply because, think about this. Let's imagine that this is a LAN or it's a room, and in that room, there's only 30 hosts and there's no other space for any other host. Well, something that will throw this completely out of the water is, imagine now you're going to be running virtual machines on these hosts. And on some of those virtual machines, you don't want to actually NAT through the virtual machine software, but you want to bridge through the virtual machine software. As soon as you start bridging those virtual machines, they're going to need their own IP addresses. And suddenly you may have 30 physical hosts, but you've got 60 hosts altogether because 30 regular hosts and 30 virtual hosts. So real world, we have to be extremely careful about what we do in terms of how we do our subnetting and how we assign our blocks of subnets. Questions? Okay, everybody's good on that? Okay. Well, I'm going to jump forward and spend just a few minutes talking about IPv6. We won't get through this whole chapter today, but we'll do a little bit today. But the big thing is, why do we need IPv6? Well, it's because IPv4 is already exhausted. There are some places in India that are actually going through 4 to 6 different levels of NAT. So in other words, before you ever get out to the internet, you're NATed up to 6 times. Now imagine how hard it is to do any type of end-to-end traceability or end-to-end connectivity when you're being NATed that many times. You'll notice here, all the dates are, we are out of IPv4 addresses everywhere except for Afrinic, and they are pretty much out now as of 2020. The big thing about IPv4 and IPv6 is most people don't realize it, but it's already turned on all Windows machines. It's typically being turned on most Linux distros now. We've got what we call a coexistence through a dual stack method. In other words, the machines are running both IPv6 and IPv4, and that is probably going to be the best way we're going to run in the near future until we decide to go completely IPv6, which will have to happen eventually simply because of the number of devices that are being rolled out on the internet. But dual stack, that's what it means. You've got both stacks running on the devices, including your routers. Tunneling is where you take and you may have an IPv6 only network, and then you tunnel that through an IPv4 only tunnel. So in other words, you do IPv6 inside of IPv4. And then last, we do have what's called NAT 6-4, and there's a translation where you actually can NAT between IPv6 and IPv4. It is frowned upon greatly. In fact, it's something that there was a lot of discussion about even doing away with it, but it is something that is still there as a possible item for the near future. What does IPv6 give us? We've already talked a little bit about it. It's 320 undecillion addresses, I think it is. So enough IP addresses for every single grain of sand on the planet. It is a 128-bit address written in hextets or 16-bit segments. Okay, so we have, as you notice here, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 hextets. 8 times 16 is 128. Each one of them has a decimal value of 0 to F or 0 to 15. So it's, again, being hex, it's 16 based. So 16 binary digits. The preferred format, there's all types of different formats, which you'll see here. This is the long, very long format for addresses. In other words, it's each hextet that is separated by colon. But we've got all kinds of ways of making this shorter. So we've got some rules you're going to need to learn in order to shorten these addresses make it easier for you to type in. And also just easier to actually look at. So first off, we can always omit leading zeros. So in our examples here, this 2001 0 db8 quad 0, all ones, quad 0, quad 0, quad 0, 0, 200 can become 2001 colon db8 colon 0, all ones, colon 0, 0, 0, colon 200. And since these are leading zeros, we know that a single zero has been left out here, 3 zeros here, 3 here, 3 here, 3 here, and 1 here. So again, you can omit leading zeros. The other thing you can do is what's called the double colon. Now, a double colon can replace any single contiguous string of zeros. Okay, now it's important. You can only ever have one set of double colons in an IPv6 address, because otherwise you wouldn't know how many hextets it represented. So if we have this example right here, okay, you will see that we have these 3 contiguous quad zeros. So we can actually change this very long address to 2001 db8 0, all ones, quad ones, colon, colon, 200. And since we know this is supposed to be 8 hextets, we know this is 1, 2, 3, 4, 5 hextets. So we know this double colon represents 3 sets of zeros, 3 hextets of zeros. Likewise, look at this one. We've got quad zeros at the end, so we can actually become 2001 db8 0, 0, colon, AB00 colon, colon, again representing 3 sets. You could not, however, put a double colon here and a double colon here, because at that point, if you did that, okay, so let's think about that. If you did that right here, so let's get rid of all this, my low-tech notepad. Let's imagine if you had this. Okay, 1, 2, 3. So there's 3, so we know we got to have 5 more hextets somewhere. So is this 3 zeros and this 3 sets of zeros and this 2 sets? Or is this 2 sets and this 3? You don't know. So that's why you cannot do that. You must only have 1 set of double colons to represent contiguous zeros. Now, it would be completely legal to do this. Oops. Crazy, but completely legal. Because you got 3, 4, 5, 6, and you know that's 7, 8. But that would be a way to do it. It's just not a preferred method to do it because it's not the shortest possible way of doing it. So you could just definitely do this right there. Okay. So you can omit leading zeros, and all 0 segments, one of them can be replaced by a double colon. So let's look here. We're just omitting leading zeros. This will be 2013, 0, 1, 2, 3, 4, 5, 6, 7, 89, AB, C, D, E, F, 0, 1. Okay. And really the compressed format, there's really not any compressed format other than what we've already got there. So you'll see there, you could get rid of the 0 here. Is the only thing you do is put a colon there to do compressed, which doesn't really gain you much. It just replaces one set of quad zeros. This is a good way to just do all kinds of different examples, and it just keeps putting in different examples for you to be able to do. Okay. All right, folks, I'm going to end here. We're going to pick up with address types. In fact, I'm probably going to have to take this and make it into a lecture and just send it out to you because I'm not going to be able to meet on Thursday afternoon. But I will get you a lecture out for the rest of these and send it out to you, and we will go from there. Are there any questions? Let me stop my sharing here. Are there any questions? Please, again, I am working on grading, so I'm going to get caught up on grading. I'm just a little bit behind, so I apologize. Any questions? Everybody good?
No questions.
Okay. Is a quick question. I have a question for everybody. Is NetLabs working okay for everybody?
Yes.
Yes, I haven't had a problem with it.
Okay, good, good. I knock on wood. I do know this Friday morning from 6 a.m. to 7 a.m. we're going to have a campus-wide internet outage. It's probably not going to last for about 30 minutes, but they're going to take the network down to do some work for an hour. They've given us an hour window. So if you're online trying to do labs from 6 to 7 a.m. Friday morning, you will not be able to do so. So just be aware of that. I haven't seen very many on at that time, but you know, just in case, just so you know. Okay, I'm gonna stop.